Hello students, in this lecture we are going to use the order of magnitude analysis to derive the boundary layer equations over a flat surface. The same equations which were given by Prandtl in order to investigate the flow within the boundary layer region. Okay, there are in fact two different methods for deriving the boundary layer equations. The first one is the order of magnitude analysis, which we are going to discuss in our lecture, and the other one is the asymptotic analysis, in which we consider the asymptotic version of the set of Navier-Stokes equation for larger than all number. Okay, so let us go to our problem. The problem is what we have already studied in the last lecture. In the last lecture, we discussed the concept of boundary layer using this flat surface. Okay, so the flat surface was kept in a free stream u infinity, and the boundary layers developed. This is the edge of the boundary layer, and these are the different sections of the boundary layer. All these terminologies we have used in the last lecture. Okay, so we are now interested in this thin region. As I told you that the boundary layer region is a thin region, so we are now interested in this thin region, and we want to derive a set of equation which is valid only in this thin region, not beyond that. Okay, the set of equation derived by Prandtl were not applicable for the flow outside the boundary layer region, but they were only applicable for the flow within the boundary layer region. Okay, so let us consider the steady two-dimensional flow over a flat surface, and the fluid is Newtonian with constant fluid properties. Okay, so what we have, the equation of continuity for a steady two-dimensional flow, incompressibility condition is also there. So incompressible fluid flow, for incompressible fluid flow, the equation of continuity is given by this: del u del x plus del v del y equal to 0. So this is your equation of continuity. Now the order of magnitude analysis works on the idea that in an equation we must have the terms which are dominating in nature, or which have higher order of magnitude in respect to the others. So that let us understand this with the help of this. Let us suppose you have three forces. The first force is F1 equal to 100 Newton. The second force is F2 equal to 200 Newton, and there is another force which is F3 equal to 2 Newton. So if there is an equation governing or the balance involving the balance of these forces, let us suppose there is an equation which is F1 plus F1 equal to, let us suppose, F2 plus F3. Okay, now let us suppose this is some balance of forces. This equation represents some balance of forces. Okay, so now if you look at F1, let us suppose we are scaling down all the terms of this equation. So what we are doing, we are dividing it by, let us say, 100. Okay, so if we are dividing it by 100, means your F1 is nothing but 1, F2 is nothing but 2, and F3 is 0.02. Okay, now you see your F1, if you write down in you can write down 1 into 10 to the power 0. This you can write down as 1 into 2 into 10 to the power 0, and this you have to write down 0.02, or you can write down this one as 2 into 10 to the power minus 2. Look at the difference between the exponents. Bases are same, we have kept the base same, bases are same, the exponents are different. 0, 0, this is minus 2. It means what? It means what? F1 and F2, these two forces are comparable, whereas this force F3 is not comparable, or you can say that F3 is negligible in comparison to F1 and F2. So in this equation, which was some force balance equation, in this equation you can say that the F3 can be neglected in comparison to F2 and F1. Okay, this is the situation. So you can say that F1 and F2 are of same order of magnitude, whereas F3 is not of same order of magnitude, and the order of magnitude of F3 is lesser than the order of magnitude of F1 and F2. Okay, so that F3, the effect of the force F3 can be completely neglected in this equation, and we can simply write F1 equal to F2. So this is the idea of order of magnitude analysis, and using this idea we will be able to derive the Prandtl's boundary layer equation over a flat surface. Okay, so like we scale down here with the help of a digit, a number which was 100, we need the scaling factor of for each of the quantities that are involved in the equations. So what are the quantities involved in this equation? The quantities are u, x, v, y. So we have to identify which scaling factors we need to use in order to scale down these physical variables. Okay, so the fluid velocity in x direction can be scaled with the help of the free stream velocity. So u is of order of magnitude u infinity. Okay, the length along x-axis can be scaled down with the help of the length of the plate, which is some characteristic length. Okay, why this length is significant? You already know, as the length grows, the boundary layer thickness increases actually. Okay, and in y direction, what is the significant length we have? We have the boundary layer thickness. So what are we left with? We are left with the velocity in the y direction v. We do not have any characteristic velocity in the y direction, and therefore we keep this v as it is, or we assume that v is scaled down by v infinity, let us suppose, and let us find out what is the value of this v infinity. Okay, now according to order of magnitude analysis, the order of magnitude of this del u del x term is u infinity upon L, and the order of magnitude of this del v del y term is v infinity. V infinity is the assumed order of magnitude of v, and what is the order of magnitude of y? It is delta. Now because this is according to this continuity equation, this term gets the sum of these two terms is equal to 0. It means these two terms are somehow comparable, and they are nullifying the effect of each other. Okay, so that u infinity upon L is of order of magnitude of v infinity by delta. Okay, so we don't have to consider the negative, because they are nullifying each other. We don't have to consider the negative sign because we are only considering the magnitude. So therefore the magnitude of this should be comparable to the magnitude of order of magnitude of this. Okay, so u infinity upon L is of order of magnitude v infinity upon delta, and from here we will be able to write down the order of magnitude of v infinity. So the order of magnitude of v infinity is in fact u infinity delta upon L. If you use this order of magnitude of v infinity, this equation will be satisfied. Equation 1 will be satisfied. Okay, so what did we get? We get that the order of magnitude of V infinity is U infinity into delta by L. Okay. Now we move towards the X. I told you in the last class that the boundary layer equations are nothing but an approximated version of the Navier-Stokes equation. So for this type of problem, we are starting with the X component of the Navier-Stokes equation. So the X component of the Navier-Stokes equation is U del U del X plus V del U del Y equal to minus 1 by rho del P del X plus nu del square U del X square plus del square U del Y square. Okay, because the flow is steady, we have not considered the time dependent term. So these are, if you can recall, these are the convective terms, convective acceleration term, this is pressure terms, and these are the viscous terms. Okay. Now we have already derived what is the order of magnitude of V, that is V infinity is given by U infinity delta by L. Now this delta by L is appearing in this V infinity. This has a physical significance. If you assume delta by L less than very less than 1, it means what? Your delta is very less than your capital L. What is capital L? Capital L is some length along the plate or length of the plate. And what is delta? Delta is the boundary layer thickness. It means what? The boundary layer thickness is confined in a thin region along the surface of the plate. Okay. So this is what is important to us. We want to consider the flow boundary layer region as a region which is confined within a very small region or within a very thin region along the surface of the plate. So that we will proceed further by taking delta by L very less than 1. Okay. We won't consider delta by L equal to 1 or delta by L greater than or, because those cases are not of our interest. Now, so this is our X component of the boundary layer equation. As usual, we will try and evaluate the order of magnitude of each of the term present in this equation. Okay. So now U del U del X, the order of magnitude of U del U del X is given by, what is the order of magnitude of U? It is U infinity. What is the order of magnitude of U? That is again U infinity. So you get U infinity square. And what is the order of magnitude of X? It is L. So U infinity square by L is the order of magnitude of U del U del X. Now we come at the next term. What is next term? The next term is V del U del Y. So the order of magnitude of V del U del Y is the order of magnitude of V, that is V infinity. The order of magnitude of U, that is U infinity. And what is the order of magnitude of Y? That is delta. So V infinity, U infinity by delta. And if you substitute the V infinity value that you have already obtained, U infinity delta by L, so you get U infinity square delta by L upon delta. And if you cancel the delta, you will get U infinity square by L. So V del U del Y is again U infinity square by L. So what do you get? You get that in this equation, these two terms are of same order of magnitude. These two terms are of same order of magnitude, and in comparison to each of them, in comparison to each other, both of them are having equal weightage, or none of them should be neglected in comparison to the other. Okay. Now we move towards the right hand side, and in the right hand side we start with the viscous terms. The viscous term, so what we have noted down? We have noted down that the convective terms are of order of magnitude U infinity square upon L. So the left hand side is completely of order of magnitude U infinity square upon L. See, we don't have to write 2 into U infinity square by L because 2 doesn't matter. like we explained here, it was 200 newtons, so 2 was not of any significance, because in order of magnitude analysis we only consider the in fact, if it is 900 newton, then also both are comparable. Okay, so in the left hand side, the convective terms are combinedly is of order of magnitude u infinity square upon L. Now we consider the right hand side, nu del square u del x square. So nu is nu, u is u infinity, x square means L square. So nu u infinity L square is the order of magnitude of your first term of the among the viscous terms. Okay, next term is nu del square u del y square. So this is nu u infinity upon delta square. Now we want to study how does these two terms behave in respect to each other. So we find out the ratio of the order of magnitude of these two terms, del square u del x square and del square u del y square. So the ratio of order of magnitude of these two is given by nu u infinity by L square, nu u infinity by delta square, and this will give you delta by L whole square. And we have already assumed that delta by L is very small because we want to study the boundary layer region, which is very thin. So if delta by L is very small, it means the order of magnitude of the nu del square u del x square term is very small in comparison to the order of magnitude of nu del square u del y square term, and therefore nu del square u del x square can be neglected in comparison to nu del square u del y square. That is, nu del square u del y square is the dominant viscous term in equation number 2. Okay, so whenever this, you can say, whenever this term is present in the equation along with this term can be neglected. Okay, the effect of this term can be neglected. Okay, now we are left with the pressure gradient term, and in order to identify the order of magnitude of the pressure gradient term, we will have to use the Euler's equation. If you use the Euler's equation and you equate the pressure gradient term, you will be able to find out that the order of magnitude of the pressure term is rho into u infinity square. Then what is the order of magnitude of this? Minus 1 by rho del p del x. The order of magnitude of this is 1 by rho u infinity square upon L. That is, the order of magnitude is u infinity square upon L. So the pressure gradient term is also u infinity square upon L. So what is the x momentum equation now? The x momentum equation is del u del x plus del u del y equal to minus 1 by rho del p del x plus nu del square u del x square. Okay, this is the equation that we have at the moment. Let us see what happens with the y component of the momentum equation. Okay, now we have the y component of the momentum equation as u del v del x plus v del v del y equal to minus 1 by rho del p del y plus nu del square v del x square plus del square v del y square. Again, we will find out the order of magnitude of each of the terms. So if you find out the order of magnitude of u del v del x, it is u infinity square delta by L square. What is the order of magnitude of v del y? It is u infinity square delta by L square. So both these terms are comparable to each other. They should not be neglected in comparison to each other, none of them. Now if you move to the right hand side, the viscous forces, again, as we did in the previous equation, this term can be neglected in comparison to the viscous term del square v del y square. by the same logic what we used in the x momentum equation. So whenever these two terms are present together, del square v del x square, or you can say that del square del x square can be neglected in comparison to del square del y square in general. Whatever is here, that doesn't matter. Okay, so it means what? We have this equation as 0. Now we want to compare each of the terms with this viscous term and the pressure gradient term. Now we have noted that LHS is of order of magnitude u infinity square delta by L square. The pressure gradient term is of order of magnitude u infinity square by delta. So let us compare the pressure gradient term with the left hand side. So convective terms in the left hand side by pressure gradient term, we have obtained the ratio just like we did in the case of x momentum equation to compare the pressure gradient term with the two viscous terms we compared by using a ratio. We are again using some ratio of convective terms in the left hand side by the pressure gradient term in the right hand side, and the order of magnitude of this ratio is u infinity square delta by L square, u infinity square by delta, and if you simplify this you will be getting delta by L whole square, which is again by our assumption is much less than 1. So what do we conclude? We conclude that the convective terms in the left hand side is very small in comparison to the pressure gradient term in the right hand side. So what do we get? This term should be considered 0. This term should be considered 0 whenever this term is present in your equation. Okay. Now what is left? We are left with two terms. This del square v del y square and this del p del y term. We will find out the ratio of these two. The dominant viscous term, that is del square v del y square, pressure gradient term. So nu v infinity by delta square upon u infinity square by delta. If you simplify this, you will be getting nu into v infinity by delta u infinity square. And if you perform some manipulation, you will be able to write down this as nu u infinity by L. By using the value of v infinity, we get this. And if you want to write down, this can be written as 1 by Reynolds number. What is Reynolds number? Reynolds number is defined as u infinity L by nu. So this is 1 by reciprocal of the reciprocal of the Reynolds number. Okay. Now it is interesting to note that what we assumed that delta by L is very less than 1, and it is interesting to note that this implies 1 by Re is also very smaller than 1. This we will actually prove later on after completing this analysis. Okay, so if delta by L is very less than 1, that is the boundary layer region is very thin, then 1 by Re is also very small. This is in fact very important because in practical purposes you will not be able to find out the thickness of the boundary layer or the length or the characteristic length. Even if you will be able to know the characteristic length, the thickness cannot be known. So how can we find out whether the boundary layer region is confined within a thin region or not? That depends upon the value of the Reynolds number. If 1 by Re is very small than 1, then the boundary layer region is confined within a very thin region adjacent to the surface of the plate. Okay, so what we note that delta by L very smaller than 1 implies 1 by Re very smaller than 1, and if 1 by Re is very smaller than 1, then we know that the dominant viscous term should be neglected in comparison to the pressure gradient term. So what we get in this equation? This equation is also, this term is also 0 in comparison to the or you can say whenever this pressure gradient term is present, this term can also be equal to 0. So all the terms in this equation is 0 except this pressure gradient term. So what do we get from the y momentum equation? The dominant viscous term can also be neglected in comparison to the pressure gradient term. Hence, the y momentum equation is reduced to del p by del y equal to 0, and which gives you that the pressure gradient pressure is not a function of y. Okay, pressure is not a function of y. Or if you move in the vertical direction in the boundary layer region, the pressure doesn't change with respect to y. So that means whatever is the boundary layer region, whatever the pressure is in the boundary layer region, that pressure is due to the pressure that is outside the infinity, and that also is function of x. So the pressure outside the infinity we are denoting by P infinity. Let us say this is denoted by P infinity, and that P infinity itself is function of x. Okay, so pressure is not a function of y within the boundary layer region. That is, pressure does not vary within the boundary layer region as we move in the upward direction, and therefore let the pressure outside the boundary layer be P infinity. Then we have del u by del x plus del v by del y equal to 0. This is the equation of continuity. And y equation, from y equation we get del p del y equal to 0. So there is nothing in y equation now, we are only getting this information. The x momentum equation is u del x plus v del u del y equal to minus 1 by rho. In fact, it was del p del x plus nu del square u del y square, but this del p del x can be written as dp dx because the pressure is only function of x, it is not function of y. And again, whatever pressure is there, that pressure is due to the pressure outside the boundary layer region, which is P infinity, and therefore we are writing this term as minus 1 by rho dp infinity dx. So del u del x plus del v del y equal to 0, and u del x plus v del u del y equal to minus 1 by rho dp infinity dx plus nu del square u del y square is these two equations are known as the Prandtl's boundary layer equation over a flat surface. Okay, these equations, if you want to find out the solution, this has to be solved using suitable no slip condition and the far conditions. Now there is one more version of this Prandtl's equations, that if you apply the boundary layer approximation. So boundary layer approximation essentially means if you are going beyond the boundary layer region, or if you are crossing the edge of the boundary layer, what happens? So if you are crossing the edge of the boundary layer, it means what? Your u becomes u infinity. So this is u infinity del u infinity del x. There is no velocity gradient in the y direction. Okay, and if there is no velocity gradient in y direction, then this del square u del y square is also 0. It means what? Minus 1 by rho dp infinity dx is u infinity du infinity dx. Okay, so u infinity du infinity dx equal to minus 1 by rho dp infinity dx. So if you substitute the value of this pressure gradient term in this equation, we now get del u del x plus del v del y equal to 0, continuity equation unchanged, and from the x momentum equation, u del x plus v del u del y equal to u infinity du infinity dx plus nu del square u del y square. This is another version of your Prandtl boundary layer equations. Now, if your u infinity is a constant velocity, then this term is completely 0, and we are left with this equation, u del x plus v del u del y equal to nu del square u del y square. Using this equation, now you can prove what we claimed initially. What we claimed, delta by L very small implies 1 by Re, is also very smaller than 1. So u del s plus v del u del y equal to nu del square u del y square. This is what we have derived, and in order for this equation to be valid, each of the terms should be of same order of magnitude. So LHS, we have already seen that it is of order of magnitude u infinity square by L, and the right hand side is of order of magnitude nu u infinity by delta square. So both of them should be comparable. So u infinity square by L comparable to u infinity by delta square, and this implies u infinity L by nu is order of magnitude of L by delta whole square, or Re is order of magnitude of L by delta square, or 1 by Re is of order of magnitude delta by L whole square. So whenever delta by L is very less than 1, 1 by Re is also very less than 1. Okay, so we have completed the proof of the boundary layer equation. And if in fact, whenever you want to scale down Re, you can scale down with delta by L by delta. And if you want to see the skin friction or order of magnitude of the skin friction, the skin friction coefficient is given by tau w equal to mu del u by del y at y equal to 0. So the order of magnitude is mu u infinity by delta, and the skin friction coefficient is given by Cf tau w by half rho u infinity square. So this is the order of magnitude of this is mu by rho u infinity by delta u infinity square. So after manipulation it gives you nu u infinity by delta, and we have already seen that delta square by L is of order of magnitude nu infinity by L. Okay, so for a local x, if you want, you can write down delta square by x is of order of magnitude nu by u infinity, and therefore Cf is nu by u infinity under root u infinity by nu x, okay, equal to under root nu upon u infinity x, and this is equal to Rex to the power minus half. So you can see the coefficient of skin friction is scaled by Rex to the power minus half. Okay, so in problems involving fluid dynamics, whenever you will find out the coefficient of skin friction, you will be able to see that you should find out some square root of Re into Cf equal to that some like for example f double dash equal to 0, right? And so on. Okay, so you can say that this is the scale factor for the coefficient of skin friction. So this completes our analysis of order of magnitude. We will discuss the solution of this boundary layer equation in the next lecture.